So we learned chi-square test for independent, and that's for examining the correlation between two categorical variables. Okay, so we use a Pearson's chi-square test, and also there's a Spearman's chi-square test. That actually, if you have data that are not bivariate normal, so it failed the normality assumption, and we have a non-parametric version for it. Right? But if you have two quantitative variables, right, last time we mentioned this so-called against Pearson's correlation coefficient, right? So Pearson actually contribute a lot in statistics. So, and that Pearson's correlation, there's a simple Pearson's correlation that when you have a set of data, bivariate data, you compute, and both are quantitative, you compute the bivariate correlation, right? And that number, we call it R, sample correlation. If that number is very close to +1 or -1, we say that there's a strong linear correlation, right? The positive and negative linear correlation. And usually when we try to check or study the correlation, we will first make a scatter plot, right, to see whether we do have a linear trend or not, because that Pearson's linear correlation coefficient, right? That's a number helping us to see how strong a straight line or linear correlation is. So if you have data that is nonlinear but has a very clear trend, right, that means there is a correlation, right, just not linear. So the way we can deal with it is that we do a little transformation, right, transform the data and make it linearized, right? Then you compute the Pearson's correlation and then use that number to report the correlation, right? So that's what we did last time, all right? So here I have a picture here. This shows a pretty clear straight line correlation. We can compute the Pearson's correlation for it, right? We can also test for zero correlation, right, to see whether the Pearson's correlation coefficient is significantly different from zero or not. And a lot of times people do that, right? So if you reject a null hypothesis, that means the correlation is not zero, right? Statistically significantly different from zero, right? So once we found that there's a strong linear correlation, and sometimes people will probably like to do prediction, right? So you have a very strong straight line pattern. We can fit the straight line to describe that pattern. And theoretically, or ideally, in classical regression approach, right, with a normal assumption, we like that line passes through the mean, right, of response, right, at any fixed level of predictive variable. So if you have, for instance, this problem, we have a weight and height variable, and you wish to use height to predict weight, okay? From this chart, I think we can visualize, all right, using the chart to kind of help you to estimate. So if I ask you, if I have a person height than 60, what would be this person's weight? By looking at this scatter plot, you know that weight probably is between like 70 to 100, maybe 15, in that range, right? Because at this fixed level of 60, your weight varies, right? Some are here, some are below, and then probably if the distribution pattern for weight is normal in this level, then you should have more points in the center, and usually that's very close to this straight line. Okay, so if you observe this pattern at a different fixed level of height, and you saw that the pattern is almost like a bell shape all the way, right, throughout the range of this data, then we say, well, then it satisfies the classical regression and modeling assumption that you have normally distributed response at any fixed level of predictor variable. So height is predictor variable, weight is what you wish to predict, or we call it response variable. Okay, so that's what we're going to focus on today, right? I'll actually review today. Last time we talked about testing correlation. Today we're going to talk about how we can do the prediction. Okay, so I'm going to quickly. So when we're doing this, I hope you know the term. What's the response variable? What is explanatory variable? Right? Response variable is sometimes we call it outcome or dependent variable. Okay, this is usually the reason we like to do the modeling. We believe that there's some changes in weight, difference in weight, and what actually causes the weight so different. When you believe that, it's because of height. People with different height have different weight. So we use height to explain variability of weight. So in this case, the weight is response variable. Your height will be explanatory variable. Right? So it's important to understand these terms. And I think you studied this earlier in this course in the beginning of the semester. But it's very important now when you're doing the regression. You've got to be able to identify what is your response variable, what is your predictor or explanatory variable. Okay. So let me quickly go through this. Right? We did this before. So there's a way we're going to fit a straight line, right, for the data and the result from fitting the straight line equation. You get an equation like this. Right? Your response variable, the expected response variable value, is the y-intercept plus the slope of a straight line times the x variable, right? And these two numbers can be estimated, right, through the regression analysis or using the least square estimation, right? And software can do that for you very quickly, right? So, and the graph like this, kind of again repeating what I just said. Okay, at different level x, we expect that the variability for response variable all behave like bell shape. And a line passes through the mean of these bell-shaped distribution of the response variable. Okay. So the example that we used last time was this handgun registration. Right. So we have like 14 pairs of data, and then we try to predict the number of people got killed based on number of handgun registration. Right. So there is a formula to help us to get this beta and alpha, based on the sample means for those x. X is predicted variable values. Y are those response variable value. And you have a standard deviation for response variable value and a standard deviation for the predicted variable value. And also you can have the Pearson's correlation for these pair numbers. Now let's go back to that data, right, very quickly. This is your data. These are the x and y. So you calculate the standard deviation, the mean for these x and y separately. Right, and use that into a formula like this, right? So you have mean and standard deviation and Pearson's correlation. We can estimate the alpha and beta. Right? So once you estimate the alpha and beta, you can actually, so this is actually the calculation of alpha and beta. You can find a regression equation, right? So y is equal to the alpha plus beta times x. This is the prediction equation. So next time you have a handgun registration number here, plug it in here, you can get the expected number of people got killed based on this regression prediction equation, right? Some of you probably have started your homework assignment, right? You probably have gone through this already and practice how to write this, to analyze the data and then find out this model. Okay, then you can use that for prediction. Okay, or estimation, I should say. And an important thing you need to know is that once you found that model only good for the range of data that you use for building that model. Right? So in that data, your data ranging for number of handgun register ranging from 400 something to 700 something. So this model is only good for the data is between 400 something to 700 something. Right? Outside of range, you don't have data, so you cannot use the model you come up with this data to predict whatever is outside. Right? You don't want to extrapolate. Right? So this is a picture kind of try to show you that idea. I have these data point and from x ranging in this interval, and I found a model that best fit my data. Right? So later on, if I have an x value that is outside of this range, you don't want to extend this line or still using this equation to predict it, because when x getting higher, right? You have more people having handgun, maybe less people got killed because people don't want to pull handgun out to point at other people. They may be shot by other guys, right? Because everybody have gun. So in that case, the trend may go down. You never know, right? We don't have any information in this range. It's dangerous to just extrapolate it, right? If you really extrapolate it, you're going to make a huge error there. Okay, so keep this in mind. You only can do a good prediction or estimation when you're predicting something that is within the scope of the data you use to build a model. That's very important. Okay. You may have seen that people do extrapolation like in forecasting, right? You see people forecasting the economy, forecasting all kinds of things, right? Those are some kind of extrapolation. But when they're doing that, they actually watch some kind of pattern in the past, right? Not just actually using. So there are different type of modeling techniques, I should say. I don't want to get into too deep, right? So actually confused. So there are other methods to do the extrapolation. Just by simple linear regression, it's really not good enough. Okay, so be careful on that, right? Don't do extrapolation. all the regression analysis method that we learned in this course, reviewing this course, linear regression, multiple regression, logistic regression, all right, none of this suggests that you do extrapolation. So if you try to do a prediction that your X value is not within the scope that you use to build a model, it's out of that range, then that prediction would be horrible, I mean, terrible. That would be questionable. So be careful on that. Right? Don't try to do that. If you really want to do that, you have to tell people that you try to extrapolate, and there is a risk in doing that. Okay, good. So I hope that makes sense. So how do we actually build this regression model? Now, earlier we went through the scatter plot, right? And before we examine the correlation between two quantitative variables, we say that we tried to study Pearson's correlation, and that Pearson's correlation actually is for describing the strengths of a straight line regression, right? So we observe the scatter plot, we realize it's linear, right? So it kind of helped us to see that, well, if you try to predict the expected response variable, right, by looking at a chart, that expected response variable actually is the linear function of the predictor variable, right? So that's how we actually decide on this term. Anytime we're doing a regression, right, or in classical approach of doing regression, usually what we do in the first step is try to hypothesize what is the relation pattern, right, between the response variable or expected value for response variable that you get, how that related to the predictor variable, right? So you want to guess this one. But we look at a chart, we know that it's linear, right? So we actually fill that in. We say, oh, it's alpha plus beta x, because what you expect in the behavioral response variable is actually a linear function of a predictor variable, right? And also another assumption in linear regression modeling is that this error term here, right, is normally distributed with constant variance. Now, to explain this assumption here, this is similar to this chart that I just drawn, right? That's the idea that I shown you in this graph. We assume this is going to explain that error term, right, the epsilon. They should be all have the same shape and bell shape, right? That's the assumption behind the classical linear regression modeling technique, right? So making that assumption, we can then have be able to develop the sampling distribution of this model and be able to do hypothesis testing, and we'll be able to do confidence interval estimate when we're doing prediction. So this assumption is very important, right? And in classical approach, this is actually assuming normal with a constant variance. Okay, so that's actually the actual model, right? We call it first order simple linear regression model. You have one predictor variable, one response variable, and you want to model their relation, right, using some mathematical model, adding the random component in there, right? This is a mathematical deterministic part of the model. This is the random component of the model. Okay, so wow, I have this here. I forgot that. All right, so that's a model assumption, right? So when we have the data, we fit our data with a straight line, so we get that particular line there, and then you have, assuming that there are 3 data points that allow you to actually fit this straight line, right? So if you use this straight line to do prediction, now using this existing 3 data point you use to build a model, and you plug in the x coordinate for this point, actually the location for y is over here on the line. So there's a difference between the actual y value that you observe and also the y value that you get from that regression equation, right? So the difference between that y value you calculate from a prediction equation or regression equation and what you actually observe, this is called residual, right? Yi is actually the number you observe, right? Yi hat is actually the value you calculated using that regression equation at that same level of x. Okay, so these numbers are residual, and they are important values, right? It helps us. Each data value has a residual. It helps you to actually access or do the model diagnostic to see whether the data satisfy the model assumption for you to run the linear regression or not, right? So that's very important, right? So here is just an example. I observe our data, x is 460 and y is 21. If I use 460 to plug it into this regression equation model, I got a 16.01, right? So this 16.01 is actually on that regression line. This goes back to that same Handgun registration problem, right? This is one of the data points. If you plug in 460, you should get 16.01. That's from the regression line. But what I actually observe is 21. So the difference between those two is the residual. Right? You use what you observe, subtract what is predicted. That's 4.99. So each piece of data you can calculate a residual. Okay, and actually we predicted value we usually use a notation y hat. So you saw that in the regression equation too, right? So if we can calculate all these residual for all the data point, right, and square them and then sum them up, we call this residual sum of squares. Okay, and this is a number actually can help us to estimate the variance that we mentioned earlier for that model. Okay, so that sum of square error or sum of square residual divided by n is sample size minus 2. This number give us so-called mean square error. And this number is, we call it unbiased estimator for estimating that sigma squared that we assume in that regression model. Remember we said the epsilon follow a normal distribution with mean 0 and constant variance sigma squared. So residual sum of square divided by sample size minus 2 give us a good estimator for estimating that common variance. If you take square root of that number, that's called standard error for this regression model. Right? So that's a term I hope some of you can understand. Right? A lot of time people mention this standard error. We learned standard error in testing mean, right, t-test. Here also the standard error for regression. Okay, and usually when you run regression, software will give you some different sum of squares. So just to help us understand the variability due to different source of different places, right? Like variability may be due to the regression model. Variability may be due to just the random error, right? The nature of the data, okay? And variability may be due to just the response variable itself. And when we do the regression model, we actually try to use the regression model to describe the variability in the response variable. We try to predict number of people got killed, and then the number of people got killed, that number varies, right? Why does it vary? Right? So we can use this regression model source of variability to explain the variability in the response variable by using the explanatory variable through the regression model and also using the estimate for those random error that happen in all the analysis, right? Things are all different. Right, so it's always variability exists in the data. And so there's so-called a total sum of square that is actually measuring the variability for the response variable value. So then this is almost like getting the sample variance for the y number of handgun register, right? You use the y minus mean of y squared. If I divide by n minus 1, that's really the sample variance of the response variable, right? But here we just collect all these sum of square due to the response variable. So that's y value minus mean of y squared and accumulate that. That's called response variable variability. And there's also the error variability. That's what we just mentioned, residual. So sum of square residual. That's sometimes we call it residual sum of square. Sometimes we call it sum of square error or error sum of square, right? And then there's a regression variability, right? This line here is like a regression line. How this line varied with the overall mean of the response variable. So you measure the difference from the predicted variable value and then mean value for response and accumulate those differences, right, by squaring them and add them up. That's called regression sum of square. And in fact, that there's a relationship between these three sum of square. That is, total sum of squares is equal to the sum of square due to regression plus sum of square due to error. Okay. So here, actually, is so-called the ANOVA table. Most of the time, if you run the regression analysis, you will see this table. And this table is very similar to the ANOVA table that you saw when we do one-way ANOVA. Okay? And you have two sources of variability to explain the total variability of the response variable. One is regression sum of square. One is just error sum of square. Right? Now, if the regression sum of square is high, that means most of the variability for your response variable is accounted for in your regression modeling. That also means that the regression model is good. Okay, that regression model is useful. So there's an F-test that's based on the estimate of sum of square variability from regression and then estimated variance from error. Ratio of those two give you an F-test. So if the variability from response regression is much higher than variability due to random error, this F-score will be high. That also means what regression model is useful, right? So sometimes we say when we look at this ANOVA table, we can actually found a test of utility of the model. That means whether the model is useful or not by this f-test. If this f-test score is high, that means its right tail error will be small, right? Which its right tail error will be the p-value. P-value is small. So if that p-value is very small and less than 0.05, for instance, all right, and we're going to say, wow, the regression model is statistically significant for this prediction, right, at 5% level significant, right? So I just quickly explain this because you're going to see this table, right? You're going to wonder, what this table for? What's the p-value from this table for, right? That's for helping us to understand how good this model is. Right? It's useful even, right? So if you look at this sum of square ANOVA table, there is a sum of square due to regression, right? If you use sum of square due to regression divided by sum of square total, the sum of square total is sum of square total from response variable. This ratio gives us a number called coefficient of determination, right? This number helps us to understand the proportion of the variability from the response variable that is explained by the regression. So if this number is high, this number, of course, will be a number between 0 and 1, right? If this number is high, that means the regression model is explaining a high proportion of variability in the response variable, which means it's good, right? So sometimes when you do this modeling, you need to do some transformation because probably the model doesn't fit the data quite well, a linear trend. You may want to transform the data, linearize the data, and you try different transformation, right? And how do you decide which one is best? Well, the one that gives you the higher R square will be the better one. Okay. So here I actually define this coefficient determination. That is the proportion of variability in the response variable that can be explained by the explanatory variable through the linear regression model. So the higher the proportion, the better. Okay. So for that regression, the Handgun registration data, we do have an R square. It's 0.886, right? That's coefficient of determination. That means what? About 89% of the variability in the response variable, right, can be explained. It's explained by the explanatory variable through this regression model, so which means that's pretty high, right? And of course, this is an output from SPSS, right? I made a slide for this from using R, but actually I think it's not complete enough, so I didn't use it. But you'll find out similarity there. Okay. And the bottom table, this one is actually the ANOVA f-test. They report the p-value for the f-test, and that p-value again, I told you that's for testing the utility of the model. This p-value is less than 0.05 means what? That model is useful, right? So the predictor variable is useful in predicting the response variable. And usually then when you run regression, you will get this coefficient estimation table. And I will go through this with you, right, in a little bit, showing you how to use a R commander to run this. But you will see a output that is for coefficient estimation. So you see here, there's a constant and number Handgun register. That means what? This is really the alpha hat, right? And this 0.125 is really the beta hat. So you found this two number on the coefficient table. You can just plug it into this regression expression to get the prediction equation, right? Y hat is the predictive value. The predictive value of the response variable is this negative 41.43 plus 0.125 times the explanatory variable value, right? So this becomes the equation that you can use for prediction, right? And also at the end of this table, you have this T and then SIG in SPS as P value. When you run the R command, you will say C P value or probability value, right? So this tells you that I can perform t-tests for testing whether the alpha is equal to 0 or not, and also testing whether the beta is equal to 0 or not in this regression equation, right? Now, what if alpha equal to 0? If alpha equal to 0, that means you have a regression that cuts through the origin, okay? And if beta equal to 0, that means what? There's really no correlation between y and x, right? Regardless of what value you have for x, y stay at the same level. Right? So when we run this linear regression model, it's very important to check this number and the p-value for testing this significance of this, in this case, we number Handgun register. Right? If you have a p-value that's so small, that means what? That beta is not 0. Right? So beta is meaningful. That also means what? This predictor variable is useful to be included in the model. Right? So we'll look at this p-value to decide whether the second p-value to decide whether this model is useful or not. In fact, here, if you go back to the formula for predicting beta. That beta actually is function of correlation, Pearson's correlation. Right? So in fact, testing this beta equal to 0, it's similar. It's exactly the same as testing whether that correlation coefficient is equal to 0 or not. So they will be exactly the same. Okay. So that's a very important thing you want to look at, right? This thing, and also this is just a simple linear regression. So this p-value actually help us understand whether this model is useful or not. So the conclusion from this, all right, this should be similar to this utility of model test of utility, right? Because this tells you that model is useful. That also means what this beta is not equal to 0. So this one should be also extreme. You should have a very small p-value for that. Okay. Okay. So I hope that makes sense. So you have to run a series of t-tests when you run the regression. All right. So there's t-tests over here. So you learn several t-tests. Right? You learn one sample t-test for mean. You learn two independent sample t-tests for comparing two means. Right. So when people ask you what test you use, you don't want to say, I'm going to do a t-test. You got to tell people what kind of test you're using. There's so many t-tests for different purpose. Okay. Likewise, chi-square test, you learn so many different chi-square tests. Right? Each chi-square test has its purpose. So if you want to communicate with people, you don't want to say, I want to run a chi-square test. You got to tell people, oh, I'm going to run a McNamara test, right? Or run a chi-square test for independence and so forth. So these names are important. These terms are important when you try to communicate with people. Okay, good. So this is actually a quick explanation of the beta, right? If testing beta. So there's a test for testing beta equal to specific value or not, all right? So testing the beta coefficient. So of course, a special case that what we use in regression is testing whether beta equal to 0 or not, right? So a general form for that t-test is your beta hat minus a beta under null hypothesis divided by, this is a standard error of a beta hat. And it can be calculated. This SY given x, this is actually the standard error I just mentioned, right? Remember we have a, using sum of square residual, divided by n minus 2, we get the mean square error, which is the estimate for the common variance sigma square. And this is the square root of that mean square error. Right? Divide by, this is sum of square for x value, right? Predicted variable value. And that'll help you to calculate the standard error. Of course, in this class, you don't have to worry about all these calculations. Software will take care of it, and you will just get this outcome, that p-value, right, and t-test score, right? And what you need to do is just interpret that, right? But this slide just tells you how it is done, right? You have a t-test for it. So if you want to test for alpha equal to 0, there's a t-test for testing whether alpha equal to 0 or not. Okay. Also, there are confidence interval estimate for prediction. So once I come up with that prediction equation and want to do prediction, right? Now, statistically, when you try to do prediction, we always do this confidence interval, right? So there are actually two formulas here. One is confidence interval estimate for predicting the average response. So for instance, in that Handgun registration, you want to predict that for those area or regions, when Handgun registration is at 460 level, what is on average number of people got killed? If this in general, you want to estimate average number of people got killed for that kind of Handgun registration level. So you use this formula, and software will take care of that. I will show you how to do that. Now, if you try to predict an individual case, for individual region, if the Handgun registration is 460 level, how many people will be killed? Then you use this formula. So if you try to estimate an individual case, you're going to have a larger standard error. You're going to have a larger margin error, right? Because you try to just estimate one point. Right? If you want to estimate the average, of course, your standard error will be smaller. Just like when we try to do confidence interval estimate for mean, right? You're estimating mean, you have a smaller margin error. If you try to estimate a particular individual's value, right, in that population, you will use a region that covers 90% or 95% of whole distribution, right? That's actually a larger interval. Okay, so hope this makes sense. When you try to predict individual case, your interval will be larger than when you try to predict an average. Average will give you a smaller interval. Right? But anyway, you have these formulas, but software will take care of this for you. Just in case those who want to go into statistics, right? This is actually maybe useful information for you. And here is a graph I could kind of show you how the confidence interval look like. When you try to estimating mean, you look at these two bands, a little bit curved inside towards the line. That's the confidence interval band for estimating mean. And the outside band is confidence interval estimate for individual. So if you cut it at a different level, you'll find out that, of course, estimate mean you have a smaller interval than estimated individual point. Okay. You also find out that when you get closer to the center of gravity for this bivariate data, like somewhere over here, close to mean, your band is narrower. Right? That makes sense when you look at this data, this formula. Standard error has the value. This is the value that you wish, x value that we should predict for a response. When this x value is very close to mean, this term is very close to 0. So the standard error will be very close to 0. So hopefully this formula kind of help you to understand that reason why. Right? But, okay. Also, when we do the regression, simple linear regression, we also, every time we do it, if we really want to do prediction and also test for significance, you like to check these model assumptions that I mentioned earlier, right? Whether the epsilon, the error, is normally distributed with constant variance. Okay. Also, you want to see whether actually the model fit the data well, right? Do we really have linear trend, linear relation between x and y? So one quick way to do it is doing residual plot. You plot the residuals, right? And this is actually the original data. Residual almost like tilting this line a little bit, make it a horizontal line, right? Something like this, okay? So you see the behavior of all these data. In fact, when I plot this data, I actually plot the standardized residual versus the standardized predicted value. Now, the reason that people like to standardize residual because you know the normal distribution, right? So these standardized residuals, this are almost like a t-score or z-score, okay? It measures how many standard deviation are these data points in terms of residual away from the mean of the residual, which is 0. Okay, so if you have a score that is beyond 2 or 3, that means that data value is very far away from the model. That would be an outlier. Okay, and also when we observe this residual plot, we like to see these data scatter without seeing any pattern. Hopefully, they're uniformly spread from the left to the right. Okay. And also probably more data point cluster closer to the center, and when it gets further away from the center line, you get less and less. This kind of suggests that you have a normal distributed data. I'm sorry, not data, but error. Okay. If you spread uniformly from left to right, that means what? Equal variance assumption is also good. All right. So we can use the residual plot to help us to check the assumption. Right. If it's uniformly spread from the beginning to the end, that also means what? The model actually explained the trend very well. Right? If you do see data like scatter up and down and up with very clear trend, that means what? There's some trend that has not been explained by the model or interpreted by the model yet. Right? So that means your model is not so good. You probably want to refit the data. And this is one situation like that. Right? You make scatter plot, you look like this. That means what? Your model is not good. Right? You have a trend probably nonlinear, and you use it, try to fit the linear pattern. Also, sometimes you make a scatter plot, you see the spread of the data not the same. The left side you have a smaller spread, right side have a larger spread. So it's not uniform in variance. That's not good too. All right. If you try to do prediction, you have to make some adjustment. So there are methods to take care of that. In this class, let's not worry too much about it. Right. If you go into more advanced class, like regression class, you probably learn more about this. Right? And sometime when you try to do regression and you see data don't have a linear trend, right? And so if you try to calculate Pearson correlation, you're going to find Pearson correlation very small. When you try to fit a straight line, that straight line doesn't make sense in describing this data, right? And you try to check normality assumption, it fails. When situations like this happen, you would linearize the data, right? And this particular data actually transformed the GDP. This data is for modeling the relationship between female life expectancy and GDP, and try to use the GDP to predict female life expectancy. Right? If you want to use a straight line to fit the data, it's definitely not good. But if I actually transform the GDP by taking log of this GDP value and replot the scatter plot, actually I get a trend that's more linear. Okay. Now I see a more linear trend, and it makes me feel better to fit the linear regression through it, right? So if you transform the data and then do the fitting, you have a new equation like this. Your y hat is alpha hat plus beta hat times the log of the GDP, right? So the log of GDP is kind of like a new variable, right, in this whole regression analysis. Hope that makes sense, right? If you do see nonlinear trend, okay, you want to do some transformation. And student will ask, some people will ask, what kind of transformation should I use? Do I always use log? Well, usually people try log, exponential function, or take square, a square root. People start with those, right? There are some technique actually you can use a specific function, right, to actually model data. Actually, there are some criteria in there, right, that help you to get a function to best fit your data. But the function usually look not quite reasonable, or it's very strange, right? And when you model these data and the relationship between two variables, oftentimes, right, it has like an exponential or log kind of pattern, right? So usually that's what people do. When you have data trend goes like this, go up and turn right, usually you will try to do a log transformation. Okay. If you have data actually go towards right and then go up, then you would do an exponential function. Apply e to the x, right? So apply exponential function to the data, right? But this is all by experience. It's all try and error, right? You try different transformation until you feel that this data really look linear. Or if you try to figure out a Pearson's correlation, and Pearson's correlation very high, or square of the Pearson's correlation, we call it coefficient of determination, right? If that number is very high. So if you try different transformation and the one that give you the highest, that's probably the better one, okay? Better one doesn't mean it's correct one, okay? When you do the modeling, usually this is what people say, right? There's no correct model, but there's better one, right? You just do the best you can to find a better model, right, to describe your data. Is that really the true model? No, there's no true model, right? There's better model. Okay, so hope this makes sense to you, right? So this is about simple linear regression, right? So when you have a quantitative response variable, you want to predict it or study the correlation between another quantitative variable to this quantitative response variable, right? And we study Pearson's correlation, and then sometimes we will like to do prediction. We do this simple linear regression. Okay. On Springboard this week, we have these data. Now the data that I put on Springboard, one is Excel, one is SPSS. You can download either one of them. Right? Our commander can import any of these. So maybe I just download this. Let me see if I can save this. I can save that, right? So save it, download, okay. In the meantime, I'm going to try to also save these other ones. I'm going to save the weight, high, which we will use that later on, okay. Wage by height, wage by age and height, okay. And you probably like to download this following two. These two are Excel, so let me try to download these. And also download these. Okay, let me show you what I have downloaded. I have downloaded this first two links from SPSS. Okay, and then over here for logistic regression, I downloaded disease and low birth weight parity. Right, I download these two. So if you have the laptop, you can download those first. Okay, so I got those. I'm going to run the just mean the R commander. Okay, so I'm going to run the R commander, load the package. I'll just take the R commander. Can you see it clear? Okay, good. So I'm going to load the data, import SPSS, right? I downloaded SPSS, so I'm going to import SPSS. I'm going to call that data set 1. I'm going to look for that data that I download, right kill, right? So I click on that, and then either one, edit data. So I got that data, right? Register and kill. Register means Handgun register. Kill means number of people got killed. Okay. I hope everybody follow what I did. Okay. First, go to Springboard, copy down this reg kill, and weight by age height under SPSS. If you want to download Excel, that's fine too, right? These are two that I download. I always download the disease and low birth weight parity. Okay. And so after I download those, I go to Archimedes, I go to data, import data, and select from SPSS data. So to import SPSS data, right? And you go there and look for that data and open it, right? So you should have this data now, okay? So both are quantitative. Now remember, before you run this regression analysis, simple linear regression, or you try to calculate the Pearson's correlation, you always want to do this: graph, scatter plot, and plotting. Since we are predicting number of people got killed, so the number of people got killed will be the Y variable. That's a response variable. And then number handgun register will be the X variable, right? There are options here. Let's not worry about these options, right? Just look at the scatter plot, right? So what I did, scatter plot, choose kill, and register, okay? And just click OK. So I get my scatter plot. So that's a scatter plot, right? The trend is very clear linear. So that's great. That's it, right? Now, if you like to study the Pearson's correlation, or actually Pearson's correlation test for zero correlation, you click statistic summary correlation test. Okay, click on that and just hold your control key and select both of them. Now, here, Pearson's product moment, that's a Pearson's correlation test. And doing two-sided tests, testing whether that Pearson correlation equal to 0 or not, right? So that's good. Just click OK. You get this Pearson's correlation test. Right? You have a t-score 9.6755, degrees of freedom 12, and p-value that's 5.10 times 10 to the negative 7. So that's definitely less than 0.05, right? So you're going to reject the null hypothesis of zero correlation and support that the Pearson's correlation is statistically significantly different from 0, right? So that's how you test for zero correlation. And if you want to run regression, right, go back to this graph. You want to predict number of people got killed by using Handgun register, right? Then what you do, come to statistic, fit model, okay, and you do linear regression. This is the option that you can actually run the correlation, a model, one response, quantitative response variable, one quantitative predictive variable. So you click on that. Want to model the number of people got killed by Handgun register. Right? So select this as a response, select this as an explanatory. So you got to know what's the meaning of response variable and what is the meaning of explanatory variable and be able to identify them, right? So that you can run the model properly. If I had the register as a response variable, then you can't really do prediction for the number of people got killed, right? So you've got to have them checked properly. And then you click OK. And you see this is a coefficient estimation part of it, right? You have a p-value for testing intercept. Now, our command use the term intercept, or R use intercept, and SPS use constant, I think, right? So this is the same thing. And this is the p-value for testing whether the handgun registration variable is significant or not. And you have a p-value less than 0.05, very small, right? 5 times 10 to the negative 7 power, so very small. And here you look at the coefficient. This is exactly the same as what you saw earlier in SPSS output. Exactly the same thing. So with these two, you can write the prediction equation, right? This is the alpha hat. This is the beta hat, right? So if you recall, the alpha hat and beta hat, this equation, right? That was the equation. Where is it? Yeah, the equation here. Negative 41 and then 0.12, okay? So that's really exactly what we saw here, okay? Then you see this p-value here at the bottom. That's a p-value for testing model utility from f-test, right? So you get the, again, this number, if you compare this number and this number, they're the same, in fact, because this is actually a regression model with one predictor variable. So this f-test is the same as testing beta equal to 0. It's the same as testing that Pearson's correlation equal to 0. It would be the same, okay? then you have the R squared, 0.8864, right? Exactly the same as what we have from SPSS. Okay, hope that makes sense. Right? Over here, this is that SY given X. This is that standard error. The tech squared, this would be the mean square error that I was showing you earlier. So this is how you run the regression, okay? And if you want to do model assumption, you can actually click model, check model assumption. You can look at the graph, and it will give you a basic diagnostic plot. If you click on that, supposedly should give you some picture. You see, where is it? Here, right? So this is that residual plot, okay? And thing on the right is a checking normality assumption. Remember, there's a QQ plot for checking normality assumption. If all the dots follow pretty much a straight line pattern, that means the normality assumption is okay. Now this data, it seems not too bad, right? They're about on a line diagonal. Then there are other measures. We haven't talked about this. We probably won't talk about this. We just want to get some basic idea. But when you do the regression analysis, usually you want to pay attention to also some extreme value here. So I have data like this. Let me see. I have data look like this, all right? So it's pretty good. I can fit a straight line from the left-hand lower corner to the right-hand upper corner. But if I have to have a data that is outstanding here, that data will be very influential, right, to the whole modeling. If I have a data point over here, this line going to tilt, right, towards this data point. If that data point is an error, then your model will be horrible, okay? So anytime we run the regression analysis, we also want to pay attention to some of the outstanding data. Some of them probably will be very influential from the model. And things like this is kind of helping you to understand those, right? But let's not worry about it. Right? I guess from this course, you want to know the general idea about regression, right? If you really want to do more serious analysis, you want to take a regression class, a more advanced regression class. Or if you have a project, it won't hurt to find a statistician to help you, okay? So there's graph here that can actually help us to understand do the model diagnostic. And remember, how do you do that? Once you build a model, you have this regression arc, reg model.1. That means there will be a lot of information after you run the regression saved under this name, reg model 1, right? So when you have reg model 1 here, you click model and click graph, basic diagnostic plot, it'll do that for you. And there are so many other diagnostic, and there are also confidence interval estimate for parameters, and there are some hypothesis testing, and there are many other things. There are tests for heteroscedasticity. That means tests for equality of variance, right? So there's so many tests that you can perform, right? And there are also these that allow you to actually do the model checking. And sometimes people do stepwise regression when you have many predictor variables, not just one, so many of them, and you don't know how to pick the better one. There are stepwise regression approaches that you can do, okay? So that's for the regression, a simple. So